Hello everyone. Today we'll discuss about physical chemistry, the gaseous state. Okay. So the kinetic theory of gases, the postulates, the points of the kinetic theory of gases already have been given to the group. You can note from that and you can easily understand because these things have already been discussed in your first year or class 11th. We will now derive the kinetic gas equation. Okay. Derivation of kinetic gas equation. Derivation of kinetic gas equation, that is PV is equal to 1 by 3 mn c square, right? PV is equal to 1 by 3 mn c square. Okay, so now we have to consider we have to assume something, then after we will derive the equation. Okay, that means consider a cubical box containing 1 mole of gas. 1 mole of gas. The cubical box has sides of L centimeter. Each side of the cubic box is L centimeter. Okay. Consider second assumption. This is the second assumption. Consider a molecule of the gas of mass m. As we know from the kinetic theory of gas, some postulate says that any molecule of a gas has similar properties. Its shape, size, volume, mass is all identical if we are considering the same gas, right? So whatever molecule you choose, that will have that same mass m. Say we are considering hydrogen. Any hydrogen molecule has the same mass. Okay. So consider a molecule of the gas of mass m moving with velocity c. Okay. So let us figure out. This is the box. Okay, this is the cubic box having each side L centimeter. Side of the cube is L centimeter. A molecule with velocity c is moving. There are 1 mole of gas. Right? Okay, 1 mole of gas is present. We have considered a single molecule. From the single molecule, we will reach at 1 mole. Let me tell you one important thing. What is the plan of our derivation? How can we derive this PV is equal to 1 by 3 mn c square? Our plan is rate of change of momentum, rate of change in momentum is equal to force. This is our plan. Rate of change in momentum is equal to force. So we have to consider one molecule. its momentum, its change in momentum. From that we have to calculate the rate of change in momentum of single molecule. From that the rate of change in momentum of all the molecule. Then we will proceed to the PV is equal to 1 by 3 mnu square. As we know that the velocity can be resolved in 3 axes, like these are the 3 axes. If this is x, if this is y, if this is z, velocity in the x direction, that will be cx. Velocity in the y direction will be cy. Velocity in the z direction will be cz. We will proceed in a similar fashion. First we have to calculate considering the direction x, then y, then to z. Now we will start with, since we are concerned with the momentum, let us first start with that change in momentum, then to rate of change in momentum. Okay. And at first we will consider the direction x. You see, since the mass of the molecule is m, and if we will consider the x direction first, this direction first, then momentum is nothing but, we know momentum is nothing but mass into velocity, So mass is m, and in the x direction the velocity is cx. So mass into velocity mcx is the momentum of one molecule which is moving in x direction. That we will write. So you can take a screenshot or you can write whatever I am writing. Okay. So momentum of the molecule, before collision is equal to mass into velocity cx. That means mcx. Okay. Now this is the wall of the vessel. When molecule was here before the collision on this wall, then the momentum was mcx. When it will strike, then it will come back. It will strike, then it will come back. Okay. When the molecule is coming back in the opposite direction, the velocity is minus cx, but there is no change in the mass of the molecule. So momentum of the molecule after collision is equal to m into minus cx is equal to minus mcx. Right? Why there is no change in momentum? Kinetic energy. In one of the postulate of the kinetic theory of gas, we have considered that the collision of the molecule on the wall of the vessel is elastic. That means kinetic energy is conserved. So there is no change in momentum on the collision of on the wall. Okay. So now we will calculate before collision, after collision. So we will have the change in momentum. The change in momentum in a single collision, is equal to mcx minus of minus mcx. So this is 2mcx. So this is the change in momentum in a single collision. Okay, that too in which direction? X direction. But very importantly, you have to consider the box again. When you are considering the x direction, say this is the face A and this is the face B. In x direction, you have two faces. One is face A, one is face B. We have considered the collision, a single collision on this face A, on this face A. For that single collision on face A, we have change in momentum 2mcx. Right? Now we will calculate that what is the number of collision per second. Since we are going to calculate the rate of change in momentum, rate means with respect to time. So let us determine now what is the number of collision per second. You tell me, higher is the velocity, greater will be the number of collision. Definitely higher will be the velocity, it will move faster and collide with the face more frequently. Okay. Similarly, if the distance between face A and face B, if distance between face A and face B is higher, less will be the collision, because it has to cover a large distance, right? So we can write number of collisions is directly proportional to velocity in the x direction cx. Similarly, number of collision is inversely proportional to the distance 2L. How did we get this 2L? You see, the distance or the side of each side of the cube has been considered to be L centimeter. Between two successive collision, say this is the face A and this is the face B. We will write here. This is the face B, this is the face A. When the molecule is here, now it is not a collision. Here the molecule is present. Now it will move here, means how many distance? L, and then it will come to here. So if you want to have one collision, it is not two collisions, it is a single collision. So the molecule moves a distance L and again L, means how many L? 2L. So for single collision, it covers a distance 2L. So we will write here, for a single collision, distance covered is equal to 2L. Distance covered is 2L. So that higher number of collision is directly proportional to Cx and number of collision is inversely proportional to 2L. Right? Now we will see how this Cx and 1 by 2L can be linked to the number of collision. So we will write number of collisions made by one molecule on phase A per second. This is equation 1, this is equation 2. This is number of collision, this is also number of collision. Is directly proportional to, or similarly we can write directly equal to Cx into 1 by 2L, or simply Cx by 2L, or simply Cx by 2L. That is the number of collision made by one molecule on phase A per second. So the time factor is now ready. Using this, we can get the rate of change in momentum. Okay, so now we can write rate of change in momentum rate of change in momentum for one molecule for or by one molecule, rate of change in momentum for one molecule per second on phase A is equal to change in momentum into change in momentum into number of collisions per second, number of collision per second. This multiplication gives you the rate of change in momentum for one molecule per second on phase A. That is, change in momentum was 2 mcx, we have already calculated, into the number of collision made by one molecule per second is cx by 2l. So 2 getting cancelled, so it will be mcx square by l. But this is on phase A only, for only one collision, any one of the collision, maybe on A or B. Okay, so similarly, since the phase B is also on x direction, if it is having rate of change in momentum on A is mcx square by L, the phase B also will get mcx square by L. So similarly, on phase B, rate of change in momentum is equal to also that mcx square by L. So in the x direction, two phases are there, we have to add this change in momentum. So total rate of change in momentum on phase A and B means in x direction is equal to mcx square by L plus that mcx square by L. This gives you 2 mcx square by L. Did you get me? Okay. Now on x direction this is 2 mcx square by L. Accordingly, on y and z direction can be written. Total rate of change in momentum in y direction is equal to 2mcy square by L. Similarly, total rate of change in momentum in z direction is equal to 2mcz square by L. 2mcz square by L. So now in all x direction we have in all x, y, z, three directions we have the rate of change in momentum. So total rate of change in momentum in all three directions will be this plus this plus this. The total rate of change in momentum, the total rate of change in momentum in all three directions is equal to 2mcx square by L plus 2mcy square by L plus 2mcz square by L. So let us take common 2m by L into cx square plus cy square plus cz square. Did you get me? So By the resolution of vector, we know c square is equal to cx square plus cy square plus cz square. For this cx square, cy square plus cz square, we can put c square, square of the velocity. So this will be here, we will write since, so we can write 2m by L c square, 2m by L c square. Okay, so now this is the rate of change in momentum in all three directions, rate of change in momentum for a single molecule, in all three directions. That molecule has the velocity c, but from the postulates of the kinetic theory of gas, we know velocities of all the molecules are not equal. Thus, we will consider the molecule number 1 moves with the velocity c1, the molecule number 2 moves with the velocity c2, and so on. That means the molecule 3 moves with the velocity c3, like this. Thus, this will be developed, and total rate of change in momentum, this was for a single molecule. We will calculate the rate of change in momentum for all n molecules. So we will write if molecule 1 moves with velocity c1, molecule 2 moves with c2, and so on. That means molecule n moves with velocity cn. Then this is the rate of change in momentum for a single molecule which moves with velocity c. If the molecule moves with velocity c1, then the value will be 2m by L, c1 square by L. For molecule 2, it will be 2m by L, c2 square by L, c3 square by L. Similarly, 2m by L, cn square by L. Okay, so then after we will add all of them. So the total rate of change in momentum, for n molecules is equal to 2m by L c1 square plus 2m by L c2 square plus plus 2m by L cn square, right? So let us take this 2m by L in common. 2m by L, you have c1 square plus c2 square plus plus cn square. Okay, so this is the simplified form. Now we will develop it further by dividing and multiplying a capital N, means Avogadro number, to account for the number of mole, because we have taken 1 mole of gas. So you see, we will write 2m by L, multiply n here and divide n here, c1 square plus c2 square plus plus cn square upon n, right? So okay, so now instead of this, what we can write? We have CRMS, means root mean square velocity. Root mean square velocity means root of the mean of the square of the velocities, square of the total velocities. So let us start with total of the square of the velocity. So CRMS is equal to, so this is root mean square velocity. So CRMS is equal to, first add all the square of the velocity, means C1 square plus C2 square plus dot 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 plus Cn square. This is the total of square of the velocities of all the n molecules. So take the mean, means by total number of molecules n, right, and its root. So this is the root mean square velocities. So if you will write CRMS square, so then this root symbol will not be there. So you will have C1 square plus C2 square plus dot 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 Cn square by n, right, this one. So instead of this we can write CRMS square. Sometimes we write like this, C bar square, right. So this is 2mn by L C bar square. This CRMS square is also written as C bar square. So this, instead of this we have written C bar square. So 2mnl, so this is the rate of change in momentum for all the n molecules present inside that box, cubic box, and rate of change in momentum is equal to force, and from that force we will move toward the pressure. Okay, so this is the total rate of change in momentum, total rate of change in momentum, and this is equal to force, and this is equal to force. So once we determine the force, let us calculate the pressure. Now see, pressure is equal to force by area. This area is nothing but area of the cube. Okay, surface area of the cube. That is, you know, force is nothing but 2m by L n C bar square by 6L square. There are 6 faces. Each face has a area of L square. So 6 faces has 6L square. So force by area, this by this. So it gives you, this L comes down. So this becomes 2mn C bar square by 6L cube. 6L cube. Okay, so get 3. So 1 by 3 mn C bar square. This LQ is nothing but the V. ମୁଁ କ୍ଲାସ୍ ରେ ଅଛି, ପରେ ଟିକେ କଥା ହେଉଛି। So 1 by 3 mn C bar square by V. This LQ from dimension we know that is the velocity. So multiply V with P. So this gives you PV is equal to 1 by 3 mn C bar square. What is our required equation? So thus we derived the kinetic gas equation, and using which we can derive all of the gas laws. I will derive some of them now. So at first, this is a very interesting and lengthy derivation. Okay, so now we will move to Now we will move to derivation of